The fact that C# is strongly typed sets the stage for what I would argue is one of the biggest features of C#, which is that it exhibits all of the resilience to change and runtime safety that comes with more loosely typed dynamic languages, with the performance characteristics of statically typed, natively compiled code. Now, that parenthetical remark is one of those bold claims that I mentioned earlier, which should cause your skeptic antenna to twitch. But the proof is somewhat involved, so I'm going to leverage a bit of foreshadowing and park the native performance statement on the back burner for now, and focus here on the safety and resilience characteristics. But only just for now. I promise you that I will come back in the next module and show you exactly how C# is able to maintain the performance characteristics of native code. Consider this slight variation of our rudimentary C# program. All this program does is declare an array of integers, populated with the numbers 1 through 5, declare a variable named sum that is initialized to the integer value of 0, and then loop over that array of numbers, adding the contents of each element of the array to our sum variable. Notice that we're using the length property of the numbers variable to determine how many times our for loop should iterate. This is one of the productivity and safety features that most strongly typed, natively compiled languages don't provide. Once the loop concludes, the tally we've accumulated in the sum variable is displayed to the console. Let's switch over to Visual Studio and use this to explore one example of what I mean by safe. Okay, I've switched to Visual Studio and have a simple C# project ready that reproduces the code shown on the previous screen. As expected, if I build and run this program, the output is 15. Likewise, if I change the loop such that it only iterates 4 times as a hard-coded value, the output is 10, as expected. But what happens if I now change how I initialize the numbers variable so that it only has 3 values in it, like so? If you are coming from a C++ background, you would probably say something like, the results are undefined, or it will crash, because the C++ compiler would have generated machine code to sum up the 4 consecutive integer values that appear in memory, starting at the location occupied by the numbers variable. But if you are coming from a Java background, you would probably guess, or at least hope, that this kind of error results in an exception of some sort, indicating that your program has attempted to access the given array at an out-of-bounds location. Thankfully, C# works like Java in this regard, and an index out-of-range exception occurs. This is actually a good thing. In the case of this simple program, this kind of runtime type safety prevents incorrect output. But had we been writing into our array, and using a native language like C++, an out-of-bounds error like this one would result in memory corruption. If you're a lucky C++ programmer, that corruption would still result in an exception. But if you're unlucky, which is more typical, that corruption would go undetected for potentially quite a long time, resulting in undefined program behavior that can be exceedingly difficult to pin down. That's one example of the safety of C#. Now let's take a look at what I mean by resilience. To show you what I mean by resilience, I've set up a new application that uses a very simple 2-dimensional point structure that's been defined in a separate library. Pluralsight has other courses that go into more detail about how libraries are used in C#. For now, the important bit is that the definition and implementation of the point structure is in a separate binary, which allows it to be reused across multiple applications, including this one. All the application does is initialize a local variable called pt, set its x and y fields to initial values, and then display the result of calling the point structure's toString method to the console. Notice that when this version of the program is run, the implementation of toString returns a string that shows the xy coordinates of the point in standard parentheses notation. Now let's use this simple setup to replicate a very common occurrence in software systems, which is that a library we are using is updated to a newer version, but deployed to systems that still have the original version of the calling application in use. In this demo, deployment just means copying a version of the point library into the folder where the main application executable resides. We'll replicate that scenario by changing our 2-dimensional point into a 3-dimensional point by adding a new field that will hold the z-coordinate for the point. We're going to rebuild just the library, and then quote-unquote deploy the updated library to the location where our app is installed. If we rerun our application, which we have not changed or recompiled to be aware of the new field, the application still runs as expected, albeit with a z field of 0. This demonstrates C# code's resilience to change. When the application developer is ready to opt in to taking advantage of the new functionality available in the library they are using, they can of course rebuild and redeploy their application, and now have access to the extended functionality. This ability to maintain resilience in the presence of non-breaking changes to dependencies is a hallmark of C# and other managed languages. And to revisit the previous point about safety, should a library developer make some sort of breaking change to a type definition, which I'll demonstrate here by changing the type of the fields in our point structure from integers to strings, an exception would result, since the expectations encoded in the dependent application about the nature of the point structure can no longer be guaranteed by the runtime. If you're a skeptic or merely observant, you'll have noticed I made a claim about resilient and safe with native performance. We'll explore exactly how such safety and resilience are pulled off and revisit the native performance boast in the next module on managed execution.